Greetings everyone! Welcome to a new episode of Mr. Bioinformatics. In the 2nd century, Claudius Ptolemy, a Greek astronomer, he developed the geocentric model. What is geocentric model? It's a model that places the Earth in the center of the universe, with the Sun, Moon, and the planets moving around it in perfect circles. The model was widely accepted for centuries, but it had some problems. For example, it couldn't explain certain odd movements in the sky, like retrograde motion. What is retrograde motion? Retrograde motion is when a planet like Mars seems to move back in the night sky for a short time before turning its normal forward motion. Mr. Bioinformatics, does Mars move back? Look, my dear viewer, when we watch planets like Mars in the sky, Earth is moving faster in its orbit around the Sun than Mars, as Earth's average orbital speed is approximately 29.78 kilometers per second, while Mars travels at an average speed of about 24.077 kilometers per second. So as Earth passes Mars in its orbit, it makes Mars appear to move backward in the sky for a little while. But Mars isn't actually going back. It's similar to when you are driving at high speed and a slower car beside you looks like it's moving backward, even though it's still moving forward. People didn't fully understand this until 16th century, specifically in 1543, when a Polish astronomer called Nicolaus Copernicus introduced a new idea. Which idea did he introduce? He wrote a book called The Revolution of the Celestial Spheres, where he proposed the heliocentric model. What is a heliocentric model? It is the idea that the Sun, not the Earth, as the center of the universe. Copernicus realized that planets, including Earth, do not circle around the Earth. They are all orbit the Sun. This model made it easier to understand the retrograde motion, which is when a planet like Mars seems to move backward. I wish you didn't get lost, my dear viewer. I will go make coffee and come back. When Earth and Mars move around the Sun at different speeds, it creates the illusion of Mars moving backward, just as Copernicus described. Although Copernicus thought that planets traveled in perfect circle, later scientists discovered that paths are actually oval-shaped, which helped refine our understanding even further. Is it better that the orbit's oval-shaped, not circular? In 1609, Johannes Kepler, a German scientist, he published Astronomy Nova, where he built on Copernicus' idea that the Sun is at the center of our solar system. Kepler used precise data from Tycho, a Danish scientist known for his careful observations of the planets. Although Tycho didn't agree that the Sun-centered model, his measurement helped Kepler discover that the planets do not orbit in perfect circles. Instead, they follow oval-shaped paths called ellipses. This shape causes planets to move faster when closer to the Sun and slower when further away, as the Sun's gravitational pull varies. And here the world was asking, what force keeps planets in their orbits and controls the planets? In 1687, a scientist from England came to answer with the Principia Mathematica. Who is this scientist? Newton. You see, my dear viewer, your level is developing. Keep watching Mr. Bioinformatics. They are boosting your IQ level. Newton's law of universal gravitation, which is F equal to G times m1 times m2 over r squared, where F equal to gravitational force between the objects, G equal to gravitational constant, m1 and m2 the masses of the two objects, which are the masses of the Sun and Earth, and r is the distance between the centers of the two objects, or Sun and Earth. This law states that every object in the universe pulls on every object with a force. The strength of this pull depends on two things: how massive the objects are, the more massive, the stronger the pull, and how far apart they are. The farther apart they are, the weaker the pull. The force is stronger when the objects are closer together and weaker when they are further apart. According to Newton, gravity is an invisible force that pulls all objects towards each other. This is why planets, including Earth, travel in oval-shaped paths around the Sun. The Sun's strong gravity keeps them from flying off into space. This force also explains why moons orbit planets and how objects move in space. For a long time, people believed in Newton's idea about gravity, thinking it's a pull between objects. Newton's law worked incredibly well for centuries, explaining how planets orbit the sun and how objects interacted due to gravity. But in 1915, Albert Einstein came along and completely changed our understanding of gravity with the theory of general relativity. How did Einstein's theory change our understanding of gravity? Einstein didn't think gravity was just a pull. He said that big objects like the sun bend over fabric of space and time around them. Mr. Bioinformatics, I don't understand anything. Look, my dear, imagine a heavy ball on a trampoline. It creates a dip. That's kind of how Einstein saw gravity. Planets do not just get pulled by the sun. They roll around in the dip that the sun makes in space and time. Einstein predicted that light would bend as it passes near a massive object like the sun because the sun's gravity wraps the space around it. In 1919, British scientist Arthur Eddington, he wanted to test Einstein's idea during a solar eclipse. When the moon blocked the sun, stars normally hidden by the sun's light became visible. Eddington observed their positions and found they had shifted exactly as Einstein's theory predicted. Light bends near massive objects like the sun. This discovery raised even bigger questions about the universe. In 1920s, American astronomer Edwin Hubble, he made a groundbreaking discovery using the Hooker telescope. He found that galaxies aren't stationary, they are moving away from us. The further a galaxy is, the faster it moves away. This is known as redshift effect. When galaxies move away, their light stretches and shifts toward the red end of the spectrum, which has longer wavelengths. Conversely, if they were moving towards us, the light would shift toward the blue end, where wavelengths are shorter. This redshift showed that the universe isn't static, but it's expanding. Hubble's discovery proved that everything in the universe is moving further apart, raising a question. If the universe is expanding, where did it all begin? Hubble's finding revealed that the universe is much bigger than we thought and always expanding, helping to support the Big Bang theory. How? The Big Bang theory proposes that the universe began as an incredible hot and dense point around 13.8 billion years ago. In 1964, Arno Penzias and Robert Wilson, two physicists at Bell Labs in New Jersey in America, were working with a radio telescope to study radio signals from space. While setting up their equipment, they suddenly heard faint persistent noise coming from all directions.
Make the telescope right. Come left, Penzias, left. Also noise.
No matter what they did, they couldn't eliminate this background noise. They thought that it may come from a star, but this signal wasn't coming from any specific star or galaxy, but was spreading eventually across the sky. They realized that they had accidentally discovered the cosmic microwave background radiation that came after glow of the Big Bang.
Yes, my dear, it's also called microwave, but not the ones that you know. Why you always feel hungry or sleepy when you hear anything related to science?
It's called microwave because it falls in the microwave range of the electromagnetic spectrum, with longer wavelengths than the visible light, but shorter than radio waves. This discovery was important because it provided strong evidence that the universe began hot and dense, helping to confirm the Big Bang theory. However, the mysteries of the universe didn't stop there. In the late 1990s, two independent teams of scientists were studying distant supernovae. These are exploding stars that are visible across vast distance in space. Supernovae are incredibly important because they serve as standard candles in astronomy. A standard candle is an object with known brightness. So by comparing how bright the supernova appears from Earth to how bright it actually is, scientists can calculate how far away it is. This allows astronomers to measure the expansion of the universe and track its growth over time. While studying these supernova, the teams made a startling discovery. discovery. Instead of the universe expansion slowing down due to gravitational pull, it was actually speeding up. This unexpected finding indicated that something was driving galaxies upward at an accelerating rate. This surprising result led to the idea of dark energy. What is dark energy? My dear viewer, dark energy is a mysterious force that about 68% of the whole universe total energy content. My dear, let me tell you that we don't know much about the dark energy. What? Oh my god, there is 68% of hidden information we don't know about the universe? Exactly.
Okay, Mr. Bioinformatics, at least we know 32%, right?
My dear, wait. Don't be in a hurry. Unlike gravity, which attracts objects, dark energy seems to push galaxies upward, driving accelerated expansion of the universe. Despite its prominence in shaping the cosmos, dark energy remains one of the biggest unsolved mysteries in physics. What exactly dark energy and how does it work? That question continues to baffle scientists as we explore the universe's hidden force. At the same time, astronomers noted that stars in galaxies weren't behaving as predicted. Stars on the edges of galaxies were moving faster than they should based on visible matter. This hinted at the presence of dark matter, an invisible substance that doesn't emit light but exerts gravitational pull, making up to 27% of the universe.
Oh my god, Mr. Bioinformatics, you are telling me that 27% of the universe is made up of dark matter and 68% is dark energy? So after all of these discoveries and all the scientists' efforts, we only know 5% of the universe?
Actually, I don't know what to tell you, my dear, but yes, my dear. But the universe still holds countless unanswered questions. What is dark energy and dark matter made of? Let me know in the comment if you'd like an episode about them. And here we've reached the end of our episode. Thanks for watching. See you next time.